Hi guys, we are talking about temperature inversions and how they affect air pollution. This is 7.3. Let's go. Okay, so under normal conditions, our air temperature in the troposphere is going to decrease with altitude. So every kilometer that we go, temperature is going to drop 7 degrees Celsius. So 1 kilometer, 7 degrees Celsius, another one, 14 degrees Celsius less, as we increase and increase and increase and increase and increase going up. So that means that warm air is below, cool air is above. And the great thing about this is that because warm air is less dense than cool air, the warm air that has all of our pollution is going to dissipate. It's going to move up and move away. And so all these pollutants that we are creating will disappear over time. So it's a wonderful benefit that we have. A law in science is that pollutants go from a higher concentration to a lower concentration. So they're going to move from these areas of higher concentration down here to areas of lower concentration above. We call that dissipation. So throughout the day, we create pollutants and then they move away. Now, unfortunately, that doesn't happen if there's a cap. If I cap the container, there's nowhere for these pollutants to go. And that is essentially what a thermal inversion does by putting this layer of warm air on top of a layer of cold air near the ground. This cold air here that is full of pollutants wants to dissipate. However, it can't because this warm air is less dense than this layer here. So these molecules can't relieve and they're capped, and therefore we see really bad air pollution in our cities due to these thermal inversions. You can also see the temperature. Our temperature, as expected, would decrease, but then it actually increases due to that warm layer that is above, and then it starts to decrease again. And thermal inversion is whenever we have this warm layer that's capping this colder layer underneath. So as I mentioned, under normal conditions, pollutants can dissipate up because this less dense air can move up. However, during our inversion, this warm air is that cap, that inversion layer. And now this polluted air that is cooler just gets kind of tossed around and around and around. And so then we're not getting rid of these pollutants, we're just increasing them. The biggest thing, this may have nothing to do with our cities or our communities' pollutant level. It just means that we have no way to get rid of these pollutants. And so therefore, due to weather pattern, they just stay stuck. And we get this nasty air because of these temperature inversions. Same thing I just said. I'm getting ahead of myself here. So during temperature inversion, pollutants are prevented from moving up in the upward direction, and they build up in higher levels near the ground. Everything I just said. Okay, we have 3 different types of temperature inversions. We have radiation inversions, we have subsidence inversions, and we have frontal inversions. These are 3 different ways that these inversions are formed. Let's talk about the first one. On clear nights, our ground cools off by sending its infrared into space. So all particles are moving, and when they're moving, they emit infrared waves. So the ground is moving and it's cooling. So it's sending its infrared energy into the atmosphere, and because there's no clouds, nothing's there to block it from escaping. So that infrared energy leaves the earth and leaves the ground and moves up through the atmosphere. But then when that happens, the cool air by the ground is cool because it's touching the ground, and that convection causes this cool air to also be cold. But these first 10 meters or so, even 20 meters of air right on the ground get even colder because they're transferring their energy to this really, really, really cold ground. So we end up with this super, super, super cold bit of air in between the ground and like the first, I would say maybe 30 meters of air. So normally in the afternoon, due to our adiabatic cooling, we decrease temperature as we increase our altitude. So the closer we are to the ground, the warmer the temperature is going to be. But overnight, that air near the ground becomes super cold, colder than the air above it, because it's sending its energy to the ground. So we create this weird warm layer, and I want to show you it here. So instead of this being 15, we go from 1 to -5. Oh, so this is super, super, super cold here. And this is even colder right here. So we're decreasing temperature, creating this band of warm air right here. That is an inversion, and that is what traps pollution below that warm air. Now, luckily, radiation inversions, they tend to burn off by the late morning to early afternoon. So again, this is an afternoon. Here's our sunrise, where we are decreasing temperature as we increase altitude, which is not what we are expected. We then find this warm layer right here. This is our warm pocket of air that's going to block all the air beneath it. 11 a.m., it's not as bad. We still have a warm layer right here, and then by 1 p.m. that is gone. So the nice thing about radiation inversions is they do burn off by the late morning. So though we may have mornings of horrible pollution, because all of that pollutants are blocked by this layer of warm air, it does mean that luckily by about 1 p.m. that top warm layer will burn off, and then all those pollutants can dissipate. So these radiation inversions, they're going to start to develop about 2 to 3 hours before sunset, but they're going to hit their maximum thickness at sunrise. They usually dissipate in the late morning as the sun heats up, and then the cooling of the air can sometimes produce fog. So we will sometimes see cold bits of air, and we're like, oh, is that fog? Is that a radiation inversion? Is that pollution? It's actually all of those is what it is. So it's interesting. I have this in my hometown a lot, and you'll see this thick layer that starts in the morning, and then it will burn off normally around, or for us it's normally about 11 a.m. In order for these to happen, the ground has to be very cold. So we normally see these in the winter and in the early spring when the ground is very, very cold, especially when that top layer has like got a permafrost. Okay, so now this is a subsidence inversion. Happens when we have a high pressure system. It's kind of stationary over a city. So if you remember, high pressure system, air is pushing down. Low pressure system, air is coming up. So when this high pressure system pushes the air down, that descending air is going to get squeezed because we already have a lot of air here. So it's going to get compressed, squeezed by all the other particles. And when that squeezing happens, that compression happens, the temperature of that air is going to go up. When the temperature of that air goes up, it's going to cause this warm inversion layer. So we have hot air being pushed down onto an area, normally on top of cool air. That compression causes this air to heat up, causing a warm inversion layer. These, unfortunately, can last for weeks and weeks and weeks, for a very, very long time. Unlike the radiation inversions, where they're normally cleared by noon, these can take a few weeks, which means we are building up a lot of air pollution below. Another example of this often happens when you've got mountains by water. LA is a perfect example of this because you've got these deserts and this air moving from a high pressure system over the desert to a low pressure system over the Pacific. And this high pressure system brings the air over the mountains, compressing it and that compressed air gets warmed, so it comes on down. It's normally falling onto a very cool, cold level of air that's coming from the ocean. And so that can cause another inversion as well. So high pressure system blowing this air, that air compresses as it goes over the mountains, and then it lands right on top of a very cold layer of air coming off the ocean. So this is Los Angeles here, and you can see this is big layer here due to the inversion. Denver has the same thing, and it's also because of these mountains. The air is coming this way over the mountains, and so when it lands in this area, sometimes we have cool air from the Pacific. It will do the exact same thing, causing this inversion. Now, unfortunately, these high pressure systems can create these subsidence inversions, and they last for several weeks. So whenever you look at a weather map and you see these H's, that's a high pressure system. And that's when that air is pushing down and squeezing. So if any cold air gets trapped underneath that, then unfortunately that is an opportunity for us to have an inversion and have a lot of pollution for a few weeks, because that pollution just can't dissipate until that high pressure system moves on. And then finally, we can have frontal inversions. These happen when a cold air mass is kind of moving under a warm mass. So this normally happens at the border of two fronts coming together. You have a warm front and a cold front that somehow gets under the other one. And as it pushes under the other one, we get a lot of warm air trapped above, causing, again, that inversion. So the key takeaway here, inversions happen when I have warm air trapped above cold air. That's when we have inversions. And then that causes our pollutants to get trapped in that cold air because they can't dissipate. All right. Thanks, guys.